Okay, Joshua, hi. I'm assuming you can hear me, so if you can maybe just comment quickly to say that you can hear, then I'll start. Excellent. All right. Let me just start this. All right, so looking at the hexagon, first of all, what we were talking about yesterday was to make use of that trapezium and then finding the area of that trapezium so that we can just multiply it by 2. The formula for the area of a trapezium is the sum of the two parallel sides times by half times by the height between the two lines, the perpendicular height. So let's call that h for argument's sake. And then we would have a half times by a plus b times by h. That would be the area of the trapezium. The problem is, if we know that the length of the side, let's say, is 10 of the hexagon, the sides of the hexagon is 10, we now need to try and figure out a way of finding that length, and we obviously then need to determine h. Now we can use Pythagoras if we know the length of that side, and we do know that this down there will also make a 90-degree angle, and this will also be 10, which is fine. But now we need to make an assumption that the remaining portion of x there and x there is going to be something. And we can't say it's going to be half of 10 because there's no way to know that. So we need to find a way of figuring out how long x is going to be so that we can use Pythagoras to find the height of the trapezium so that we can use that formula. It's way too complicated. So what we can rather do is to look at that triangle over there. There are 6 of them, but just physically looking at the triangle first, we can identify one of those triangles. And I'm just going to a new sketch here. We can identify one of those triangles according to certain properties. So looking at that triangle, and then again looking at the interior angle of a hexagon, we know that we can find the interior angle of any polygon using this formula, n minus 2 times by 180 degrees, where n is the number of sides. So if you now take the hexagon, it's got 6 sides, 6 minus 2 is 4, and 4 times by 180 degrees will then give you, I think it's 720 if I'm not mistaken. And then if you divide that by 6, you will get, I'm not sure if I'm right now, yeah, this should actually give you 120 degrees. I'm just trying to think now if that's right. Dividing that by 6, yeah, will actually give you 120. Sorry, my mental arithmetic has now suddenly left me there. Okay, but we are getting 120 degrees for the interior angles, each one of them. Taking that 720, just dividing it by 6, will give us the 120 degrees. And we can construct a circle through the, with that as the midpoint, through the vertices of the hexagon. If you want, you can construct a circle. So that's a property of a regular polygon such as the hexagon, is that it will be uniform right through, and we can actually draw a circle which will then make those lines equal as radiuses. Now, since we've got that as a 60-degree angle then, and that is a 60-degree angle, because remember, the angles are being bisected, being the property of the regular hexagon, we can say that the diagonals will bisect the interior angles. We now have 60 degrees over there, we've got 60 degrees over there, which means this must also be a 60-degree angle, sum of the interior angles of a triangle, which makes that an equilateral triangle. So all three of those sides are therefore equal. So if this is 10, then every one of those sides will also be equal to 10. That's a whole deduction in its own right, but what I want to get to is the fact that if we now take a line there down, and we call that the h, which is now obviously the height of the triangle, we can say that is 10, and this will be 5. So let's call this S. Just to get a formula, we'll call that side S, which is this as well. That's S. It's the length of the sides of the hexagon. Then this will be S over 2. And then in that triangle, we now find H using Pythagoras. So H squared is going to be equal to the hypotenuse S squared minus S over 2 squared, which will give us S squared minus S squared over 4. Then we can make this 4S squared over 4 as well, which will give us 3 over 4 S squared, 3/4 S squared, or just 3S squared over 4, whichever way you want to look at it. But that's very important because this is H squared, and then if we take the square root on both sides, we'll get that H is equal to S over 2 square root of 3. And that square root of 3 will always be there, part of the property of working with the hexagon. So you've got S is the length of the side of the hexagons that you are given. So you just divide by 2, multiply by 3, and you've got the height of the triangle. So then, once you've got the height of the triangle, you can then go to the area of the triangle and say that is a half times by base times by perpendicular height. So this is going to be a half times by the base of the triangle, which is S, whatever S is, the length of the hexagon sides, times by H, which we've just calculated to be S over 4 times by S over 2, sorry, S over 2, just make sure I've got that, yeah, S over 2 times by the square root of 3, and then that 2 below the line and that 2 below the line will be multiplied to give us 4, and the S and the S above the line will multiply to give us S squared. So we've got S squared over 4 times by the square root of 3. However, bear in mind that is the area of one of the triangles. So we still need to multiply by 6. There are 6 triangles. So the area of the hexagon is going to be equal to 2 goes into 4 twice and 2 goes into 6 3 times. So it will give you 3s squared over 2 times by the square root of 3. And there you now have a formula for the area of a hexagon. You can then just simply substitute the length of the side into S, and you can calculate the area of the hexagon. It doesn't really matter what the length of the sides is, obviously. And if you forget this, you can deduct it the same way I've done it right now. But then we can also look now at the volume of a prism, a hexagonal prism. So what you need to understand about volume, and this is important about any prism, whether it's a cylinder or rectangular prism, or a cube, or hexagonal, or whatever the case is, the volume is equal to the area on which it is standing times by the height. That's literally, you can interrogate any formula for volume, and you'll always find its area times by height. And even if you have a triangular prism, such as that, for instance, then you can say, let me flip it over so that it stands on a triangle. So then you find out the area of the triangle and you multiply it by the height of the prism, which obviously would have been that side before. But it has to have vertical sides up, otherwise that formula won't work. But in this case, we've got the vertical sides. So you've got the hexagon over there. Just calculate the area with the formula we deducted before, times by the height of the prism, and then you'll get the volume. Then looking at the surface area, you'll find that area as before, remembering that there's another similar area at the bottom, and then you'll find the area of every one of the rectangles, remembering that the rectangle has got a side over there, which is the side length of the hexagon, and it's got a side over there, which is the height of the prism. So it's length times by breadth. Literally as easy as that. There you've got the area of one of those rectangles, multiply that by 6, and add to the 2 areas of the hexagon, and then you've got the total surface area of the hexagon as well.